The concept of a power budget is foundational in ASIC design. When we refer to a power budget, we mean the maximum amount of power that the chip is allowed to consume under all possible operating conditions. This constraint is established early in the design stage and serves as a guiding principle for nearly every major design decision that follows. For instance, the power budget will influence which technology node we select. Smaller nodes might offer lower dynamic power but could increase leakage. It also influences our architectural choices, such as whether to utilize more parallelism for improved performance or to maintain simplicity to conserve power. Why is this so critical? First, excessive power consumption leads to heat generation. If we don't manage this, we'll need expensive cooling solutions, which can increase the overall cost and complexity of the product. In battery-powered devices, the power budget is directly tied to battery life. Every milliwatt saved can translate to longer usage times, which is a key differentiator in the market. Reliability is another primary concern. High power can cause voltage drops across the chip, accelerate wear-out mechanisms like electromigration, and ultimately lead to device failures. So keeping power within budget is essential for ensuring the chip's longevity and robustness. There's also a constant balancing act between power, performance, and area, often referred to as the PPA triangle. If we push for higher performance, we may need to increase the clock frequency or supply voltage, both of which can increase power consumption. Conversely, aggressive power reduction techniques might impact speed or require more silicon area. The power budget helps us navigate these trade-offs intelligently. Power budgeting is a systematic process that ensures each functional block within an ASIC or SoC design operates within its allocated power envelope, supporting the overall system requirements. The process begins by defining a top-level power budget, which is typically derived from the product's thermal limits, battery life targets, and reliability constraints. Once this overall target is set, designers analyze the expected workload and activity factors for each block, using simulations or statistical models to estimate switching activity. Blocks with higher utilization, such as CPU cores or DSPs, are assigned larger portions of the budget, while less active blocks receive smaller allocations. Partitioning the design and allocating power budgets is not just about dividing numbers. It involves understanding the dynamic versus static power split and sometimes applying multi-voltage domains to optimize efficiency. Constraints for each block are formalized using industry-standard formats, such as UPF or CPF, which help automate power intent throughout the design flow. Physical design techniques such as clock gating, power gating, multi-VT cells, and voltage islands are employed to meet block-level budgets, while layout strategies like power rings, trunks, decoupling capacitors, and careful floor planning ensure robust power delivery and minimize IR drop. Power analysis is an iterative process. After initial estimates, designers run detailed power analysis tools to verify that each block stays within its budget. If violations are found, the budget may be adjusted, or further optimizations applied. This disciplined approach not only helps prevent late-stage problems, but also enables designers to balance power, performance, and area, ensuring the final product meets its technical and commercial goals.